Dear students, good afternoon to all of you. You are welcome in this class. And now we are going to discuss problems of supply and availability of nutrients. As you know that for better plant growth or good plant growth, we need adequate supply of nutrients to them so that they can absorb the nutrients and they will have sufficient levels of nutrients in them. But at certain points of their life cycle or certain points of their growth, they may not get adequate supply of the nutrients, particularly available nutrient. If adequate supply is not there, then their growth will be affected. Now we should see that why the adequate supply is not there. Sometimes there may not be sufficient supply of nutrients to the soil solution. So we will see that subject, what factors affect the supply of nutrients. And as you know that nutrients are taken up by plants from the soil solution. So you will have some idea about soil solution, and this soil solution contains nutrients in available form. And nutrients are taken up by this roots from the soil solution. Or as you know that nutrients can move, they can go near to the roots by mass flow, diffusion, or plant roots can directly take up nutrients if they are able to reach the ions or molecules. So these kind of subjects we are going to discuss. Overall, the objective is to understand the cycling of nutrients in the soil. Means what are the different routes of output and input of nutrients, how nutrients are lost from the soil, and how they come back to the soil. That is to understand the cycling of nutrients in the soil. Means it is input, entry of nutrients into soil, and exit of nutrients from the soil. So what are the ways by which nutrients are lost from the soil? Anybody? What are the ways by which nutrients are lost from the soil? Anybody?
Leaching,
Yeah.
then soil erosion,
Yes.
then volatilization,
Yeah.
denitrification.
Yeah. The other important loss mechanism is by plant uptake. Of course, we need it, but eventually the soils are losing the nutrients. Of course, that is for the plant growth, we know it, but we lose nutrients from the soil by plant uptake also. So these are the outputs of the nutrients. And then inputs, what are the inputs of nutrients? How they can come back to the soil? There are many ways they can come back. The roots will remain in soil. There may be some crop residues left in the soil, and manure, fertilizer application, fixation by free-living nitrogen-fixing bacteria, maybe by this atmospheric deposition may also be there. So there are many sources. Even irrigation water can give you some nutrients. So some inputs are there and some outputs are there, which is called as cycling of nutrients in the soil. And we will also discuss the factors influencing supply of mineral nutrients into the soil solution. So this is our subject. Some glossary means meaning of difficult words. Adsorption, the taking up or uptake of molecules or ions at a surface, particularly, colloidal surfaces, nutrients are attached, which is known as adsorption. It includes exchangeable cations and anions on the soil. Colloids, as you know, there are two kinds of colloids: inorganic colloids, organic colloids. Organic colloid is your humus. Inorganic colloids are your mostly clays. And these clays can absorb iron on their surfaces, mainly because of charges on different sides of the colloids. So some sides have positive charges, some sides have negative charges. So these negative charges will attract the positive charged ions, which is cations. Similarly, there may be some positive charges also on the colloids, which can attract the negatively charged ions. Overall, your clay colloid or humus both have negative charge. Overall, they have negative charge, but that does not mean that they have only negative charge. They also have some sites where you will find positive charge also that attract the anions. So sometimes what happens is cations particularly can enter the interlayers of the aluminosilicate clays or clay minerals, they can enter. So that is actually absorption, kind of absorption. And adsorption, you know, it is just attachment on the surface, attachment of ions on the surface. So to avoid this confusion, people have given new term, which is sorption. Sorption, S-O-R-P-T-I-O-N, sorption. So sorption means it is there in either on the surface plus inside the minerals. That makes your sorption. And when they come out, either from interlayers of the clays or from the surface, this is known as desorption. Desorption. So now I think sorption and desorption should be clear to you. Base saturation. Fraction of the total exchangeable cations that are bases, particularly calcium, magnesium, potassium, and sodium. Buffering capacity of the soil. So there are two kinds of buffering capacities. One buffering capacity is with respect to soil, overall buffering capacity of the soil, and one buffering capacity is with respect to supply of nutrients from different sources to the soil solution. That is also buffering the soil solution. So here you see what is buffering capacity of soil. Ability of a soil to resist change in concentration or activity of its constituents and its properties in response to external intervention. Means if you go for any external intervention, whether you go for tillage operations, whether you go for application of fertilizers, manures, any kind of practices you do there. So soil is not much affected. Soil remain much unaffected by these kind of interventions. Then it is buffering capacity of the soil. So for example, if you add organic matter in the soil, it will change organic matter, but change will be very, very slow. Similarly, if you add fertilizer, acid forming fertilizer or base forming fertilizer, they will not change pH in 1 year or 5 years or 6 years. It will take very long time because soil has buffering capacity to resist this change. Diffusion with respect to nutrients. Ions in the soil medium move from a point of higher concentration to a point of lower concentration. Already discussed diffusion of nutrients. The nutrients diffuse from soil solution to the plant roots, and then within the plant root also you got diffusion through which nutrients are absorbed. Ion is your atoms, group of atoms or compounds which are electrically charged. Loss or gain of electron. They have already gained or lost electron and they have a charge. That is your ion. Nutrient mobility means movement, the speed of movement, how fast they move or how slow they move. That is nutrient mobility. Ease with which nutrients move from one place to another in the soil. Soil mineral, you know, soil is made up of minerals. Variety of minerals are there. Primary minerals and secondary minerals, you know. So minerals, that is usually a constituent of the soil or a natural inorganic compound with certain intrinsic properties in soil. Can you name some minerals in soil? Can anybody name some minerals? Name of the minerals in soil. One or two names of minerals in soil. Where from these minerals come? What is the source of minerals in soil?
Said apatite.
Apatite.
Quartz,
Quartz.
feldspar,
Feldspar. Mica, you have?
Yes, so biotite, magnetite.
Okay. So you know what are the minerals, and also you have two kind of minerals, primary minerals and secondary minerals. And you know the difference in primary and secondary minerals in soil? All right. Now we go to soil solution. What is soil solution? The liquid phase of the soil which contains dissolved nutrients in plant available forms. So it is a liquid phase in the soil. It contains dissolved nutrients in plant available forms. So this I'm referring with respect to nutrients. But this soil solution may also have other nutrients or other elements which may not be plant nutrients. Like it can also have your aluminum soil solution, but which is not an essential plant nutrient. It can have some little concentration of gases also. It can have some molecules also, some salts also. So it has variety of things, this soil solution in it. But nutrients are, of course, there in this. Available nutrient, portion of any element or compound in soil that can be readily absorbed and assimilated by growing plants. That is your available nutrient. Crumb, you know, crumb is structure, a soft, porous, more or less rounded natural unit of structure from 1 to 5 millimeter in diameter. Exchangeable ions, positively or negatively charged atoms, which are ions, they are groups held on surface of a solid particle by attraction to charges of the opposite sign and may be replaced by other like charged ions in the soil solution. So you got exchangeable ions means they are mostly on the colloids, and they can be replaced by some other counterparts. A cation will be replaced by another cation, and anion can be replaced by another anions. So these are exchanges between soil solution and your exchangeable ions. Exchangeable ions, as I told, they are on the colloid. So replacement or change from each other is your exchange. These are exchangeable ions. Heavy metals, how to define heavy metals? They have densities of 5 tons mg per meter, have densities of maybe cubic meter, I think maybe cubic meter. Have densities of 5 ton, mg is your for tons per cubic meter. Yeah, or greater. So I need to check it, but it should be per cubic meter because meter has no meaning. Have densities of 5 tons per meter, cubic meter or greater. Examples are cadmium, cobalt, chromium, copper, iron, etc. Isomorphic or isomorphous substitution, the replacement of one atom or ion by another of similar size in a crystal lattice without disrupting or changing the crystal structure of the mineral. That is isomorphous or isomorphic substitution. When you study the minerals, when you particularly clay minerals, then you will find this isomorphic substitution. I gave you one example of ammonium and potassium, where they can change, they can replace each other, and their radius is same. Therefore, they replace each other. Some may be in soil solution, and some may be inside the clay minerals, and then substitution can happen. Potassium can substitute ammonium, and ammonium can substitute potassium. Trace elements. Elements present in earth's crust in concentration less than 1000 milligram per kg. It referring to plant nutrients, the term micronutrient is preferred. Generally, there is no such 1000 ppm concentration like things. It is mainly, I will tell you in the next part of the lecture, what is meant by micronutrients. Now, coming to the main subject, it was just introductory part. Now, I suggest you to read chapter 2 from Soil Fertility and Fertilizers. Each one of you have this book. So try to read from page 1 to last this chapter. Very, very important chapter for you. For many courses, this is really worth reading. Now, we start with the soil solution because nutrients will be supplied. Nutrients will be supplied from soil solution to the plants or to the plant roots. So let us know what is soil solution, because the availability of the nutrients will be affected by soil solution. How much quantities of nutrients are there in the soil solution? If our soil solution has very little potassium, then how can it supply to the plants? So there may be some reasons why we have little potassium or little magnesium in the soil solution. So those are actually problems that we are going to see. So what is soil solution? It is medium for plant nutrients. Means plant nutrients are contained in the soil solution. Nutrients are released from the soil solids. Soil solids means here particles or clay particles. Nutrients are released from the soil solids into the solution for absorption by plants and microbes. So it is not just plants which will take up nutrients from soil solution, but microbes can also take up nutrients from the soil solution. Of course, these microbes will not take away nutrients from the soil. They will bring it back, they will give it back to the soil. After decomposition, those nutrients will come back to the soil solution. Now, next meaning of soil solution is, it is water surrounding the soil particle. Water which is surrounding the soil particle means the water which has not been lost by leaching or drainage, subsurface drainage, is your solution. So it is water surrounding the soil particles. You can also say a liquid phase that contains dissolved ions, gases, and other water-soluble compounds. So you can see the meaning of solution. It can contain dissolved ions, gases, and other water-soluble compounds. Now, it transports chemical species to and from the soil particle. Means exchange of nutrients or ions also happens from soil solution. The exchange of colloids, clay colloid or humus will happen with the soil solution, cations or anions. Amandeep, you can mute yourself. Amandeep? Hello? Amandeep, you can mute yourself, please. So, I've unmuted Amandeep. Now, provides intimate contact between the solutes and soil particles. So, it is solute, the things which are actually dissolved are your solute. So, it provides intimate contact between the solutes and soil particles. Its pH influences the solubility and in turn the availability of several nutrients to plants. So pH of the soil solution is very, very important. It can affect the solubility and hence availability of the nutrients. World definition recognizes that at a molecular level, what is soil solution? So soil solution is part of a continuum of phases existing in distinct interfaces at molecular level. Means they are in continuity. Continuity of phases means solid, liquid, gas. Solutes in the aqueous means solution which is made up of water. Solutes in the aqueous phase may be associated with bound water at the surfaces of soil colloids. So you can have water on the surface of the soil colloid that can dissolve the ions or other solutes. So that is your soil solution. What happens? Free water percolating through the soil macropores. If you apply water, if rainfall is there, not all water is going to be part of your soil solution. Some water which has been leached down, that is not your soil solution. Soil solution or the water of the soil solution will be retained by the soil. Then the salts or solutes will be dissolved in that water. Now see here, This is your soil colloids or soil solids, maybe clay minerals you can see. And nearby to these particles, you can have soil solution. Soil solution. So here you can see that outside the soil solution, there may be some spaces. There may be pore spaces, which is atmosphere actually. Air may be there. And then biosphere, some organisms are also there in the soil. And your hydrosphere is your water in the soil solution. You got all the three phases and they are in continuum. Now question comes that how much is the soil solution in soil? How much nutrients are there in the soil solution? And how I can estimate or how I can know the quantity of the soil solution? How much is the soil solution in my soil, which have nutrients? So to know it, the techniques are very difficult to know to estimate the soil solution, the quantity of soil solution. Some people try with errors, lot of errors are there, but methods are there to know the soil solution. So how to separate soil solution from the soil? How to get it? For some soils may contain as little as 10% by weight of the water at field capacity. So not all water is your soil solution. So it may be as little as 10% by weight of water at field capacity. So reliable method to display solution from a column of carefully packed soils. So what can be done? It can be estimated in the laboratory. So you can take a column of the soil, undisturbed soil, sampling techniques are available. Take it to the lab, a column, and then you can percolate with the help of some liquid, alcohol or an electrolyte solution. So you can put on the top of this soil column, you can put some alcohol or some electrolyte solution so that this soil solution can be extracted down. Actually, it is leaching, kind of leaching you are doing, experimental stage, and then you can collect the solution in beakers or wherever you like. So this method has been tried by some people to extract the soil solution, and then you can know the concentration of nutrients in soil solution, because alcohol can be separated from your filtrate. The alternative is one more method is through air pressure or suction also. You can extract the soil solution. The alternative is to use air pressure or suction to displace the solution from moist soil supported on a porous membrane or ceramic filters. So options are available, techniques are available. Some techniques are really reliable, some are not really reliable, but techniques are available to extract the soil solution from the soil. Now we can see the concentration of nutrients in the soil solution. The concentration of soil solution varies between soils. The two different kind of soil will not have same concentration of the nutrients in the soil solution. So this concentration of soil solution will vary between soils depending on leaching regimes. Some soils you will have more leaching of nutrients, so their solution may not be rich or poor concentration of nutrients. Fertilizer addition, if you add fertilizer, the concentration of the solution will increase, the nutrient concentration will increase. Similarly, crop uptake, if you have more uptake of nutrient from the soil, the concentration will be diluted, or solution will be diluted, and processes that affect mineralization of soil organic matter. So you can see the availability of the nutrients. The concentration of the nutrients in soil solution is not fixed. It changes with the soil, it changes with the leaching regime or number of irrigation, frequency of irrigation, fertilizer application, nutrient application, you can call it, crop uptake, even losses. Some soils may have more losses. So then your soil solution will be less concentrated. So there are a number of factors that can affect the concentration of soil solution. Range, you can see ranges from 5 to 50 milliequivalent per liter of cations and anions together in non-saline soils, normal soils. You can have 5 to 50 milliequivalent per liter of the soil solution. This is the range. of cation plus anions, but 100 milliequivalent per liter for saline soils. In saline soils, you will have higher concentration of solute. Now you can see this table, very interesting table, relative distribution of nutrients between the common soil nutrient storage pools from USA. So here you can understand many things. First thing is that you can see the amount of nutrient in the soil solution. How much quantity of nutrient is there in the soil solution. You can see calcium, magnesium, potassium, nitrogen, and phosphorus. So see the first row. First row is for soil solution. So you can see calcium is 16 kg per hectare. 16 kg per hectare. This is in kg per hectare. So whatever soil solution is there in 1 hectare soil, in that 16 kg may be, this is just a rough idea, relative idea, 16 kg may be calcium, 4.3 kg may be magnesium, 8 kg may be potassium, but nitrogen, see, very small quantity, 0.2 kg in 1 hectare soil solution. You will get only 0.2 kg potassium per hectare. Phosphorus is also low, you can get 1.8. Now see other pools. Other pools, you can see exchange or sorption. Overall, you can see sorption, sorbed ions, quantity in 1 hectare soil in kilogram. So this can be very high for calcium, 31,900 kg per hectare. And you can see for magnesium, 8,000. For nitrogen, it is just 10. And for phosphorus, it is 135. So you can see for nitrogen, it is 10 because your nitrates are unstable. They can go for leaching and they can be easily denitrified. So losses of nitrogen are very quick. Therefore, you get less of nitrogen even in sorbed form or exchangeable form. See, organic matter can contribute about 2,000 kilogram of calcium or magnesium 1440. So likewise, you can see primary minerals can also contribute some calcium. This is the total quantity of calcium in primary minerals in kg per hectare. And you can see nitrogen. So nitrogen is not part of any mineral. Therefore, these primary minerals do not have any nitrogen, you will have 0. So from this, at least you can get some idea that what proportion of different cations or anions are there in the soil solution and other pools. Now see this list listed in increasing order of plant availability. Soil potassium exists in 4 forms. So you can see out of total potassium in the soil, you can see different pools of potassium in the increasing order. You can see increasing order of plant availability. Increasing order of plant availability. So minerals comes on the top, means their potassium is not directly usable by the plants. It is almost in the fixed form, which is about 5,000 to 25,000 ppm, or you can say 0.5 to 2.5%. The non-exchangeable, it is 50 to 750 ppm. This means so many milligrams per kg. Exchangeable potassium is 40 to 600 ppm, and then solution is 1 to 10 ppm. Very small fraction of potassium is in the soil solution, which is about 1 to 10 ppm only. Similarly, phosphorus in the soil solution is very low, ranging from 0.011 milligram per liter or ppm in very infertile soils to about 1 milligram or 1 ppm in rich, heavily fertilized soils. You can see that very small fraction of these nutrients are part of the soil solution. So do you think that this small fraction would be enough to supply the nutrients required by the crop? Yes, it is possible, because once the uptake, nutrients are taken up from the soil solution, they will be immediately replenished from other sources, maybe from the exchangeable cations or anions, maybe from organic matter. They will have to come to make it, you see, equivalent. You see, equivalent, or how to say it. I'll tell you later. Now you see the main subject is in this slide. What we are going to learn today is problems of supply and availability of nutrients. The presence of sufficient quantities of nutrient in soil does not guarantee the availability of these nutrients to plant. That you have already seen in this, that you have so much of storage of potassium in the soil here in this case, but it will never guarantee that this can be made available to the plants. Yes, it will be made available, but very slowly. There is process. So now you can see soil solution. This is soil solution. The nutrients can be taken up by the crop. Plant uptake. See the blue rectangle. Plant uptake of available nutrients from the soil. So when nutrients are removed from the soil solution, there will be shortage. There will be shortage of some nutrients of that particular nutrient. So now this shortage can be replenished or compensated by getting supply from other sources of nutrients which are in soil are cation exchange can happen, anion exchange can happen, and those cations or anions can enter the soil solution. But here exchange, you need to understand ion exchange. Ion exchange from the chapter I have already given you, because everything cannot be covered in lectures. So you see how these are changed. For example, you want to replace calcium from the colloids, then you need to take 2 hydrogen. 2 hydrogen can replace 1 calcium. Similarly, 1 hydrogen can replace 1 potassium. Then your hydroxyls can replace your anions. So you need to learn at your own. So supply from cation or anion exchange can happen. This solution can be supplied nutrients through soil organic matter. Minerals can partly also contribute. Soil organic matter is already there. Microbes, air can also contribute, rainfall, fertilizer, manures. So these are the sources that can replenish the nutrients removed from the soil solution. But some nutrients can be lost as leaching from the soil solution. And the content of nutrient, the concentration of nutrient, the availability of nutrient in the soil solution will decide the actually availability of nutrients to the plant. If you have enough level of nutrients in the soil solution, then plants will not have any shortage. And remember, this soil solution also needs water. If your water dries from the soil, then you will not have soil solution, you will not have mass flow, etc. So soil solution is very, very important. So now question comes, problem of supply. There may be certain issues related to cation exchange or anion exchange. There may be very low cation exchange capacity of the soil. There may not be enough capacity of the soil to hold enough cations or anions in the soil. Similarly, there may be very poor organic matter content in the soil. So a lot of problems can happen in the supply of the nutrients. Now you can see sources of supplying mineral nutrients to the soil solution, which is also known as buffering the soil solution. Buffering means just adding some nutrients to the soil solution which have been removed by the plant. So plants take up nutrients mostly from the soil solution. It has a small fraction of total nutrients. You have seen very, very small fraction of total nutrients in the soil solution. Nutrients removed by plants, first of all, the nutrients will be removed by plant and this pool get depleted. So nutrients readily replenish into soil solution by cation exchange. They can replenish, and this is called as buffering. This is also called as buffering of the soil solution. So what are the sources of nutrients to the solution? Sources already seen by you: soil minerals, exchangeable cations or anions, chemical compounds or certain fixed chemicals or fixed chemical compounds, like you get iron phosphates or calcium phosphates, organic matter. Now you see this picture, very interesting picture, and you can see a soil solution in the center, and you will find numbers 1, 2, 3, 4, 5. So it is very easy to explain and understand this picture. First of all, come to number 1. Here nutrient uptake is there. So soil solution will get depleted in the nutrient. And then you see number two. Number two is uptake of the plant, uptake of the nutrients. So what will happen? This plant roots will release hydroxyl and hydrogen ions. And these released hydrogen and hydroxyl ion will exchange for cations and anions. You know this phenomena. So these roots releasing your hydrogen, hydroxyl, or even bicarbonates. These can help in exchange of other cations and anions. So that is the way of nutrient uptake. Number three is that these ions can come from colloids. Exchange surfaces are there, colloids are there, so they can supply nutrient to the soil solution. But if there is shortage of ions in these colloids, then reverse exchange can also happen. The nutrients which are in excess in the soil solution can go back to the cation through cation exchange. They can go to the or anion exchange, go to the colloids. Number 4. Number 5 is your mineral solubility. So some nutrients in solution can be fixed as minerals. They can become mineral if they are in excess, if they are not in balance. And also if there is shortage of certain nutrients in the soil solution, then minerals can solubilize and they can also buffer this solution. And also you can see point number 7. Point number 7 here, 7 and 8, left side. So see organic matter and microbes. You can see they can also supply nutrients to the soil solution after mineralization. But immobilization can also happen. Immobilization means these available forms in soil solution, available form of nutrients in soil solution can be converted back or can be immobilized in the form of organic matter. And then you can see 9 and 10. 9 and 10 means some atmospheric deposition can also add nutrients to the soil solution, and some can be lost back, like ammonia volatilization, etc. You know. And see the point number 11 and 12. In 11, you can see rainfall can bring some nutrients to the soil solution, but there can be leaching also, leaching of nutrients. So this picture simply explains you the sources of nutrient supply and mechanism in soil solution for plant uptake. This is very well explained in the chapter I recommended you for reading. Now let us see some basic thing about nutrients, available nutrients. So readily, moderately, or slowly available nutrients. You will find three things here. For example, in this case, you can see this. The nutrients in the soil solution are readily available. Nutrient on the colloids or exchangeable sites are moderately available. Or you can say between quickly available to moderately available. And see mineral solubility here. They are very slowly available. The nutrients from minerals are very slowly available. So readily, moderately, or slowly available nutrients. Absorption of nutrients depend upon their forms. Form is also important. Phosphorus is speedily available as H2PO4 and HPO4, monovalent and divalent, but unavailable rapidly in tricalcium phosphate or apatite form, because now it becomes in the mineral form, secondary mineral. Nutrients in soil solution are rapidly available. So they are readily available nutrients. Nutrients on exchange complex are also available for absorption, but not quite as readily available as from the soil solution. So they come at number 2 so far availability is concerned. So readily available nutrients, availability is fastest, moderately is your exchangeable ions, and slowly available, they are in the minerals. They are in the minerals. Now see this example of phosphorus. First column is inorganic phosphorus in soil, then source, and then availability to plants. So you can see mineral P and very strongly adsorbed P. Phosphorus in minerals or very strongly adsorbed phosphorus, and what we call it occluded phosphorus occluded phosphorus. You can learn yourself what is occluded phosphorus. So the sources in soil are calcium, iron, and aluminum phosphate minerals, and very strongly adsorbed phosphorus. These are mineral B. And then availability to plant is very, very low. Now, strongly adsorbed phosphorus. Phosphorus adsorbed to clay and other mineral surfaces, availability is low. Weakly adsorbed phosphorus. Phosphorus adsorbed to clay and other minerals surfaces high. Solution P, here you have two simple forms, H2PO4 and HPO4. The availability is high. So you can see for any one nutrient, you will find some forms are readily available, some are moderately, and some are slowly or very slowly available to the plants. Now, cycling of nutrients. I discussed in the beginning, entry and exit of nutrients from the soil. So input to the soil and output from the soil is your cycling of nutrient in the soil. This is very, very important because through cycling only, we get nutrients in the soil solution. So important point is cycling of nutrient in soil is plant uptake reduces the amount of nutrient in soil solution. Nutrients adsorbed on minerals or humus get dissolved and enter the soil solution. They will supply, they will buffer or resupply the nutrients to the solution. Nutrients added as minerals or organic manures or maybe as fertilizer increase the iron concentration in the soil solution. Minerals in soil dissolve to buffer the soil solution. Now, if you have understood the things what I discussed up to now, then remaining part is much easier to understand. Now, similarly, soil organic matter will also go decomposition and it will supply nutrients. Soil microbes can absorb nutrients from soil solution and for their growth, and then they will die and they will be decomposed and they will provide nutrient to the soil solution. The biological nitrogen fixation free living organism can also provide nitrogen to the soil solution. And of course, if we see the losses, nutrients are removed by the crop harvest, loss by erosion, leaching, runoff, and volatilization losses. Now, the topic is factor influencing the supply of mineral nutrients or factors affecting nutrient availability. Means you understand what are the factors that will affect the supply of nutrients to the soil solution, or you can say supply of nutrient to the plants, or factor affecting nutrient availability. Answer is same. So there are so many factors, but I found these 7 factors as the important ones. Some people divide these factors as internal factor, external factor, and then again and again. So that way also you can study. But I simply listed these are the 7 factors which are responsible for supply of mineral nutrients, or which influence the supply of mineral nutrients to the plant, or supply of mineral nutrients to the soil solution. We start with mobility of nutrient in soil. So there are 2 kinds of nutrients. One is mobile, other is immobile in soil. I'm talking about soil, mobile in soil or immobile in soil. Mobile means how far they can move from their place. So mobility varies with ions. Now we are discussing mobile nutrients in soil. So mobility varies with ions like nitrate, sulfate, chloride, and boric acid. They are negatively charged, not strongly attracted to exchange sites. They are soluble in soils, readily move through the root zone with water. So actually why this happens? Because normally soils do not have very high anion exchange capacity. Anion exchange capacity is just like your cation exchange capacity. Normally acid soils have high anion exchange capacity, but neutral and alkaline soils have very less anion exchange capacity. So soils do not have exchangeable sites to store the negatively charged ions or anions. So therefore, anions can be easily leached down from the soil. And another interesting fact is that they are uniformly distributed in the soil because they can move from one part of soil to another part. So they are generally uniformly distributed around the roots. Mobile nutrients within the whole soil volume occupied by the plant root system are available for transport to the root in percolating and transpirational water. Means it can move through two means also. If you have applied water on the surface and your roots are deeper, then it can go along with water. It can move along with water to the deeper layer of the soils where roots may be there. And it can move upward also with the transpirational water. Or you can say with the capillary rise, it can come to the surface of the soil. Relative mobility of each nutrient depends on soil pH, temperature, moisture, soil texture, clay type, and organic matter content. So for this, you consult the chapter, how these factors will affect the relative mobility. Your soil texture, how it will affect the mobility of anions or mobile nutrients. Now see immobile nutrients. Immobile nutrients interact with mineral and organic matter surfaces, are less soluble, and do not readily move throughout the zone. So they are concentrated in patches in the soil. They are not uniformly distributed because their movement is less. So relatively immobile in soil, plant roots access these nutrients from a small volume of soil surrounding individual roots. Plants create a small zone around the root that has very low concentration of these immobile nutrients due to plant uptake. The concentration gradient allows diffusion to transport nutrients that are further away from the root surface towards the root. If the soil has a high buffering capacity for an immobile nutrient, then the solution can be replenished and diffusion continues. With a low buffering capacity solution, concentration diffusion ultimately decreases, causing a nutrient deficiency. So different soils have different buffering capacity. Here, buffering capacity means resupplying the nutrients to the soil solutions. So for example, clay soil may have high buffering capacity than sandy soils. The important points for nutrient mobility in soils are, now the main points related to mobility of nutrient in soil and availability of nutrients. The mobile anions, sulfate, nitrate, chloride, quickly move through the root zone with water. So they can escape the root zone also, but they can come near to the root zone also. The mobile nutrients are available within the whole soil volume uniformly. The immobile nutrients interact with exchange surfaces and are less soluble and move slowly through the root zone to the root surfaces. Ammonium, potassium, calcium, magnesium are more soluble and mobile than micronutrient cations. Micronutrient cations are your zinc, copper, manganese, and iron, H2PO4 and molybdenate. The knowledge of nutrient mobility is useful in deciding the nutrient management practices. Now, why we study the nutrient mobility? Because if we have the idea or knowledge about the mobility of nutrients, then it will help us in the management of nutrients. How? For example, if you know that the phosphorus moves very little in the soil, then you can go for band placement or placing the phosphorus near the seed or near the root. So that will be helpful because we know. Similarly, we know that nitrogen is mobile in the soil. So even if you apply it on the surface, it can go down to the roots of the plant. So nitrogenous fertilizer being mobile in soil could be broadcast on the soil surface or applied in bands with almost similar results. The phosphorus fertilizer should be placed in the bands in the root zone as phosphorus is comparatively less mobile in the soil. Cation and anion exchange capacity of the soil. So up to now, do you have any question, any doubt, any point of clarification? Any point, Apurva? Anything you want to ask? Achappa?
No, sir.
So,
Sir, excuse me, sir. सॉयल सोल्यूशन सर, सॉयल पेस्ट, ये अलग अलग होते हैं सर कि एक ही सेम है?
see, actually, if you take, they are different. If you
Yes, sir.
extract, they are different. If you extract the soil solution, then take its pH. It will be different from the bulk soil. So that will be actually bulk soil. Bulk soil pH is different from soil solution because here you have very small fraction of the solutes, but your bulk soil will have much higher quantity of the solutes. So no, if we say soil pH, that does not mean pH of the soil solution. That is pH of the whole soil, bulk of the bulk soil. Is it okay?
Yes, sir.
Good. Any other point? Okay. So cation and anion exchange capacity of the soil. So this is very important. It affects the supply of nutrients to the soil solution. And we can manage this, manipulate the cation and anion exchange capacity of the soil. We can manipulate it. We can increase the organic matter content. We can increase the organic colloids. And there are certain other practices like if your soils are, say, alkaline and you want to increase the anion exchange capacity, you can put some sulfur or gypsum or something like that. You can bring down the pH. So it can be manipulated, cation and anion exchange capacity of the soil. The clays and humus work as soil colloids, exchange sites, absorbing the cations and certain anions. Cations and anions exchange occur in soils between soil solution and exchangeable sites. Ion exchange is a reversible process. So reversible process, as you have seen, soil solution between and exchange or cation exchange can happen or anion exchange. Cation exchange is more important as the cation exchange capacity is larger than the anion exchange capacity in most of the soils. The process enhances availability and retention of plant nutrients. It is simple. The soils which are having higher cation exchange capacity will hold more nutrients and can supply more nutrients to the soil solution. So cation exchange capacity affects the availability of the nutrients in soil solution. Soils dominated by, this is important, soils dominated by oxides of aluminium have positive sites in acidic soils. They have more positive sites in acidic soils, and anions can be absorbed and dissolved from them. Nitrate and chloride are weakly held at positive sites of the soil colloids. They are very weakly held and more likely to be found in soil solution. Similarly, H2PO4 and sulfate are strongly bound to exchange sites as compared to nitrate or chloride. Anion exchange capacity increases as soil pH decreases. You have seen the reason in the first statement. The soils dominated by oxides of aluminum have positive sites in S. So these acidic soils are dominated by oxides of aluminum, because of which anion exchange capacity of acidic soil is higher. Now, cation and anions on soil exchange surface. Except aluminum and sodium, most of the exchangeable cations are plant nutrients. Plant nutrients. In acidic soil, the principal cations are aluminum, hydrogen, calcium, magnesium, and potassium, whereas in neutral and basic soils, the predominant cations are calcium, magnesium, potassium, and sodium. Cations are adsorbed to the cation exchange capacity with different adsorption strength. The strength of adsorption will be different, influencing the ease with which cation can be replaced or exchanged with other cations. Because cation exchange is bound to happen between soil solution and exchangeable sites. So in this case, which cation will be replaced first or which cation can be easily replaced? It will be decided by certain characteristics of the cations. So for most minerals, the strength of cation adsorption is generally represented by aluminum Al+3 is most strongly attached to the exchangeable site, followed by hydrogen. Then calcium, magnesium, potassium, and ammonium, they are held at equal, almost equal strength is there. So sometimes potassium can replace ammonium and sometimes ammonium can replace potassium. And in the end, your sodium. So sodium can be easily removed, very easily removed from the exchangeable sites, but aluminum is difficult, most difficult to remove. And you can see hydrogen. Hydrogen is number 2 here in strength of attachment. So, but its valency is 1. Normally, you can see vacancy is decreasing as the strength of attachment is decreasing. +3, then +2, +2, +1, +1, +1. It is like this. So the properties of the cations determine the strength of adsorption or ease of desorption, how strongly they will be attached and how easily they will be detached. The hydrogen ion is unique. You can say it is at number 2 because of its very small size and high charge density. High charge density, you need to remember these 3 words, high charge density in case of hydrogen, because of which it is strongly attached to the exchangeable sites. Thus, its adsorption strength is between aluminum and calcium. Now, adsorption strength for cations with similar charge. The similar charge is determined by size or radii of the hydrated cation. Hydrated cation means water has been added to it. As size of hydrated cation increases, the distance between the cation and the clay surface increases. So you can see it can be then easily detached. So larger hydrated cations cannot get as close to the exchange surface or exchange site as smaller cations, resulting in decreased strength of adsorption. So as hydration of an ion increases, so its dissociation is very fast. Now we'll take one by one. Now cation exchange capacity again. Cation exchange capacity is one of the most important soil chemical properties influencing nutrient availability and retention in soil. Very, very important. Soil cation exchange capacity represents what is the meaning of it is total quantity of minus surface charge on minerals and organic material available to attract cations in solution. That is, or simply you can define it is the capacity of 100 gram soils to hold cations. CC is expressed as milliequivalent of minus or negative charge per 100 gram of oven dried soils. You can express it as milliequivalent per 100 gram, or we also have some more unit, centimole per kg, I think, centimole per kg. The milliequivalent unit is used instead of mass because CEC represent both the milliequivalent per 100 gram of negative charge and the total milliequivalent per 100 gram of cations adsorbed to the Cs. Now we go to anion exchange capacity. Anions in solution, soil solution are adsorbed to charged sites on clay mineral edges and organic matter. You know, sometimes they are attached to the positive sides of the colloids. Anion exchange may also occur with OH groups, hydroxyl groups in the hydroxyl surface of kaolinite. Certain clay minerals, it can exchange for certain anions. Displacement of hydroxyl from hydrous, aluminum, and iron oxide is also an important mechanism for anion exchange, particularly in highly weathered soils of the tropics and subtropics. This is really very important topic for a student from soil science or agronomy. AAC increases as soil pH decreases. This is very important. You can underline it. Further, AAC is much greater in acid soils, high in 1:1 clays, and those containing iron and aluminum oxides than in soils with predominantly 2:1 clays. Montmorillonitic minerals usually have an AAC of less than 5 milliequivalent per 100 gram, whereas kaolinites can have an AAC as high as 40 milliequivalent per 100 gram at pH 4.7. So dear students, you can see here that what are the factors that will affect the anion exchange capacity. So you can see that 1:1 type of clays have more anion exchange capacity than 2:1 type of clay. And for example, Montmorillonite can have just a 5 milliequivalent per 100 gram anion exchange capacity, but if you have kaolinite, it can have 40 milliequivalent per 100 grams soil at pH 4.7. So anions such as chloride and nitrate may be adsorbed, although not to the extent of H2PO4 and sulfate. They are more tightly adsorbed than the chloride and nitrate. So the order of adsorption strength is H2PO4 greater than sulfate, nitrate, chloride. So dear student, what I am teaching you today, this is very important for your quiz exams. In many quizzes in your career related to soil science, agronomy, fertility, you will find some questions from today's lecture. Now you can see very interesting fact in this figure. In the central part, you have soil solution. The nutrients are present as anions or cations, and they are in available form. So they can be taken up by plant roots, uptake of anions and cations. So root takes up these nutrients. It also releases hydroxyl or hydrogen ions or bicarbonate ions that can exchange for nutrients from the soil solution, or that can exchange for cations or anions. And then these soil colloids, they are in equilibrium to the soil solution. Soil colloids, clays and humus, adsorb cation and anion are there. They can be exchanged in the soil solution, and it is reversible process. Now, base, the third property is base saturation in soil. So up to now, you have seen two properties. First property was mobility of nutrient in soil that will affect the availability of the nutrients or factors influencing supply. The third one is your base saturation. Now, base saturation in soil. You know what is base saturation? Means percentage of the total cation exchange capacity or total cations that are occupied by calcium, magnesium, potassium, and sodium. The base saturation is generally higher in soils of arid region than humid region. The increased base saturation in soils increases the availability of cations. To increase the base saturation, so availability of cation increases. In general, higher the base saturation, higher is the availability of cations. So this is base saturation as a factor of nutrient availability. Number 4 is buffering capacity or ability of soil to supply nutrients into soil solution. The ability of soil to resupply ions to the soil solution from different sources, maybe clays or humus. It can be defined as the ratio of the concentration of the adsorbed ion, delta Q, adsorbed ion and solution ion. Means what proportion of ion is adsorbed on the cation exchange and what is there in the soil solution. So delta Q upon delta I. Soils may vary in buffering capacity. Some may have more and others less. Generally, buffering capacity in soil increases with increasing cation exchange capacity. First thing is that buffering capacity will increase if you increase the cation exchange capacity or organic matter and other constituents in the soil, other solid constituent in the soil. The buffering capacity of Montmorillonitic clays is high, high organic matter soils is greater than that of kaolinic or low organic matter soil. Means more organic matter, more buffering capacity, more Montmorillonite clay than kaolinite, higher buffering capacity. If kaolinite dominate, then low buffering capacity. Low organic matter, low buffering capacity. Since CEC increases with increasing clay content, fine texture soils will have higher buffering capacity than coarse texture soils, mainly because of higher CEC. If exchangeable K decreases by plant uptake or leaching, the capacity of the soil to buffer solution K is lower in sandy soils. If exchangeable K decreases by plant uptake or leaching from the solution, the capacity of the soil to buffer solution K is lower in sandy soil. Means you cannot compensate for the K uptake from the soil solution immediately. The nutrient may become deficient and K fertilizer will be needed to increase exchangeable K and correct the potassium deficiency. Addition of phosphatic fertilizer will increase adsorbed H2PO4, while some H2PO4 may also precipitate as solid phosphate compound, both of which contribute to the phosphorus buffering capacity in soil. Thus, it is evident that buffering capacity is a very important soil property that strongly influences nutrient availability. If same rate of fertilizer P is added to both soils, see, very interesting fact. If same rate of fertilizer P is added to both soils or to two kind of soils, the resulting solution H2PO4 concentration will be greater in sandy than in clay soil because of high buffering capacity of clay than the sand. If same rate of phosphate is added to both soils, the resulting solution H2PO4 concentration will be greater in sandy soil than in clay soil because of higher buffering capacity of clay than the sand. Because this clay soil have higher buffering capacity, higher cation exchange capacity, so it can hold more of H2PO4 than sandy soil, which have low cation exchange capacity. Thus, in sandy soil, you will get more of phosphorus in solution than on the exchangeable sites. Alternatively, if you wanted to establish the same solution P concentration, in both soils, then more fertilizer P would be needed in the clay soil compared to the sandy soil. Again, because of high buffering capacity of clay than sandy soils. Therefore, if you remember, you must have seen the case of herbicide use. I think in heavier soil, you need more of herbicide compared to lighter soils. The dose of herbicide is more under identical condition if your soils are heavier or clay texture. So you can understand the reason for this will be why this happens. Sandy soils has low cation exchange capacity, low P fixation, and absorb less phosphate on CEC. Thus, more phosphate is available in the solution compared to the clay soils. Is it clear? This point clear to all of you?
Yes, sir.
Okay.
Yes, sir.
Okay. Now, fifth is the soil pH. Nutrients become less available to crops when soils are either too acidic or too much alkaline. If soils are too acidic, availability of calcium, magnesium, potassium decline, but availability of aluminum may be in excess. I think you know the soil pH and availability of nutrients. I will not go into much detail into it. So because this is very common, you can see one picture, how soil pH affects the nutrient availability. Now, sixth one is soil organic matter and its decomposition by microbes. So it will almost play the same role what your cation exchange is playing, or clay colloids are playing role, inorganic colloids. So this will be doing the same kind of functions as inorganic colloids do. Availability of nutrients from soil organic matter depends on microbial activity in soil. The important microbial processes are organic matter will be decomposed and it will release the nutrients. And some of these nutrients can be used by microbes and some will become part of the soil solution. So fresh plant or other organic residues are subjected to rapid decomposition. Humus component of soil organic matter resists microbial degradation and maintains optimum physical condition. So organic matter directly playing important role, supplying nutrients through mineralization, and also humus is facilitating the nutrient availability in the soil through better water relations, etc. In virgin or uncultivated soil, the organic matter content is determined by soil texture, topography, and climatic conditions. So organic matter content is higher in cooler than in warmer climate. You must be knowing it. With similar annual temperature and vegetation increases with effective precipitation. These differences are related to reduced potential for organic matter oxidation in cooler temperature and increased biomass production with increased rainfall. Soil organic matter content is greater in fine texture soil than in coarse texture soils and is related to increased biomass production in fine texture soils because of improved soil water and nutrient storage and reduced organic matter oxidation potential. This is very interesting line for all of you to compare the organic matter content under two conditions. One is fine texture soils and other is high coarse texture soils or sandy soil. Why organic matter is higher in fine texture soils than coarse texture? The number one reason is that improved water relations in clay soils. So availability of water is adequate compared to coarse texture soil where there may be deficiency of water for plant growth. So here sufficient water is available. The cation exchange capacity is also high. So more nutrient availability in this case. And further, the decomposition rate of organic matter is also low. So therefore, fine texture soils have more organic matter than coarse texture soils. Just few more slides are left. Soil organic matter contents are higher under grassland vegetation than under forest cover. These relations are generally true for well-drained soil conditions. Under well-drained soil conditions, your grassland have more organic matter than your forest cover. Can anyone tell me the reason? Yeah.
Sir, please explain this first point.
Yeah, I'm asking now from the student, why it is so? Soil organic matter contents are higher under grasslands vegetation than under forest cover. These relations are generally true for well-drained soils conditions. Okay, I know that Rimjim is not knowing the answer, but that does not mean other may not knowing the answer. So any other student? Asika,
Yes, sir.
what do you think about this?
So this is actually comparative term. If we talk about O horizon, then the organic matter would be more in case of forest. But if we talk about the whole A horizon, then grassland soil will have more organic matter because the roots of the grasses will contribute more towards the organic matter.
Excellent. And this is actually extra answer or correct answer, but what more you can say about it?
Grasslands are having, so the grasses are having adventitious root systems. So that's why, I mean, their roots are contributing more towards the organic matter than that of the forest.
Yes, but in forest also you can have, it is very general term for forest, but forest can also have your bushes or grasses, or it can also have lot of vegetation. It is general thing here. So basically grasslands are mostly found in temperate kind of climates, temperate climate, and forest cover, of course, they are there in the temperate area also, but they are also common in tropical areas, this forest cover. So maybe something with the temperature, What Astika has said very right, is very rightly said, that in forest areas, O horizon is rich in organic matter compared to grasslands, But overall, grasslands have more organic matter than forest soil, means grassland soils. That is true, but I feel, Rimjin, that it may be the difference in temperature. These grasslands are mostly in cooler or temperate kind of climate, and perhaps this forest cover is with respect to tropical kind of forest area, tropical rainforest, because here also you have very luxurious growth of vegetation. So then temperatures are high, moist conditions, so decomposition rate is faster. But litter fall is there here, because of which the O horizon may be rich in organic matter. I can say only this much, but for detail, I need to see again this Havlin reference. You have the chapter in your hand. Please do read and get clarification yourself.
Okay, sir.
We move forward now. Soil organic matter comprises organic material at all listed. You know what is soil organic matter. And the size of these components depends. I think I can leave it. So what here we want to say is that organic matter will supply the nutrients to the soil. That is the main purpose of showing. It is a factor. It resupplies the nutrient to the soil solution. That is the message here. So you can see the primary
Sir, you are not audible.
So you have muted yourself.
हो गया. Am I audible now?
Yes, sir.
Yes, sir.
Sorry. So soil physical conditions also affect the resupply of nutrients to the ions to the soil solution. So physical condition, you know, here mainly water holding capacity, soil structure. These are important. If poorly structured soils you have, mainly because of soil erosion or tillage or other practices, it will affect the nutrient supply to the soil solution. Soil erosion decreases cation exchange capacity, thus your supply to the solution will be reduced. Poor soil structure restricts the root growth and reduces the access to the available nutrients, and optimum level of soil water means a higher level of moist. So soil structure indirectly affects the water relations. Adequate moisture also increases the rate of soil organic matter decomposition. So indirectly, you see, moisture is increasing the availability of the nutrients. Also, mass flow, you know, poorly drained soils increase the solubility of minerals, making them sometimes toxic to plants. Means if you have excess water accumulation, particularly in acidic soils, then you can have iron and aluminum toxicity. Nitrates can be lost due to denitrification in flooded soil. Another loss, another negative point of flooded soils, low moisture can result in reduced nutrient uptake. So you have 2 or 3 options of water, soil water. In some cases, if you have excess water, it can affect the availability of nutrient, or too less water, it can also affect the availability of the nutrients. So overall, this lecture completes here, and there are 13 people and 3 people are still missing. No problem.